And finally, we will introduce our first speaker of the day, Nikita, who is a PhD student in the Department of Computer Science, advised by Professor Roger Grosse, which is also an advisor for UTMIST, and Chris Maddison. She is interested in self-supervised learning and trustworthy machine learning, including problems like robustness to shifting data distributions. Today, she will be sharing her work published in ICML 2023, which quantifies and estimates differences between related neural networks with applications in continual learning and influence function estimation. So Nikita, if you're ready, I will give you host access and you may guide us through your presentation.
Sounds good, thank you. Share screen. Okay, let me know if you can see my screen. Okay, great. So yeah, thanks for that introduction. I will be presenting my work called Efficient Parametric Approximations of Neural Network Function Space Distance, which was done in collaboration with Sheldon, Johan, and Roger. I'll abbreviate this to the acronym for our method, which we call LAFTER, and just for ease. So to begin with, the motivation for this paper was this question: given any two neural networks, how different are they from each other? And and there are several reasons why we might care about this. One would be continual learning. Continual learning is a setting where you are training sequentially on different tasks, and because of the shift in data distribution, something known as catastrophic forgetting is likely. So we would like to measure how much the neural network has changed in its distribution compared to a previous version of it, so that we can quantify the forgetting of previous tasks. Another application is influence functions. There's been recent work that has shown that influence function estimation is very related to how different neural networks are in their both parametric and output spaces. And we would like to measure how different a neural network that is trained on one data point versus not on that data point are different. And then lastly, another application is machine unlearning, in which case we want to take any data point and make sure that a neural network has unlearned that data point or no longer has information related to that data point. And again, measuring how different these two networks would be with or without that data point is relevant. So with that motivation, one potential answer for this could be that we can measure some discrepancy between the parameters of the network. So we vectorize these parameters and then try to measure how different those vectors are. There are some immediate issues with this. One is that parameter space can be very high dimensional. So if you have these very high dimensional parameters for neural networks and you try to measure something like L2 distance, it's very likely that basically any 2 points in this space would be more or less equidistant from each other. So we wouldn't quite get a meaningful estimate of distances between the networks. And also we do just care more about the outputs of the networks. We generally use these networks to evaluate on some inputs, and then we want to see how different their outputs are. So with that motivation, another potential answer is to measure discrepancy between the actual functions represented by the network. And by that, what we mean more formally is a discrepancy in the network's output space. So whatever outputs it generates, given some input data distribution, and the two parameter vectors that we're considering. Throughout this presentation, and if you do read the paper, function space is basically synonymous with output space. So that's good to keep in mind. So to define mathematically what this function space distance is, which we will then try to approximate efficiently, it is the distance between the outputs of two neural networks Here I say distance. More accurately, we should say discrepancy, but I'll just stick to distance now because the example that I show will be Euclidean distance. This distance is measured by a metric in the output space. So could be Euclidean distance, could be KL divergence, and that is computed in expectation over the input chaining distribution. So that in math looks like this. If you have a function f that is represented by this network, and two sets of parameters, θ0 and θ1, we would like to measure its outputs on an input x, which is drawn from some data distribution p data, and then measure you use the metric rho to measure the difference between the outputs of these two networks. And that we're calling the function space distance between θ0 and θ1 given data distribution p data. Okay, so just in practice, we usually don't have access to p data, so we approximate this with its empirical, with the empirical average over the data set that we have available, say of n points. Okay, so to estimate the function space distance, there are several methods that have been proposed, and we can broadly categorize them into parametric methods and non-parametric methods. Parametric methods depend heavily on the parameters or some information related to the parameters of the network only. So they store all that parameter information and not any data along with it. So they generally have a lower memory cost. Non-parametric methods do need to store parameter information and also some information about the data points or the data distribution, and generally incur a heavier memory cost. Parametric methods generally regularize in parameter space, and non-parametric ones try to regularize networks in function space or output space. And in practice, at least for continual learning, parametric methods tend to have poor performance. And intuitively, that kind of makes sense because they don't usually take into account the data distributions that they're computing these estimates on. And the state of the art for continual learning has been non-parametric. So non-parametric methods do tend to perform better. Okay, so in this paper, our goal is to come up with a parametric estimate for function space distance, abbreviated FSD, which is computationally efficient and memory efficient, but also performs competitively with non-parametric methods. And there are several advantages of having a parametric estimate, even outside of efficiency. One is that if you don't need to store too many data points, then that alleviates some kinds of privacy concerns also. So that's generally an advantageous thing to do. So I'll lay out the problem setting specifically for an MLP with ReLU activation functions. This work also generalizes to other architectures. For instance, in our paper, you feel free to go ahead and look at the generalization to convolutional networks. But in this case, I'll just present the MLP version to understand more easily. So if this is the definition of an MLP, we have pre-activations for every layer, which are a linear function of the activations of the previous layer. And then activations are computed as phi of the pre-activations. In this case, we'll assume phi is the ReLU function. This is a standard definition. And there's one more thing we need to define for our setting, which is what output metric we'll be considering. So like I said, we'll use Euclidean distance. And Euclidean distance can be written out as the sum of the first two moments of the outputs that you're measuring this distance between. So if Z is the output of the neural network, and delta Z is, say, Z0 minus Z1, where those two correspond to outputs of the networks θ0 and θ1, then the expected Euclidean distance can be written down in terms of this expression, which is the first two moments of these delta Z's. And that becomes relevant for efficiently computing this distance. So the actual method is what we call linearized activation function trick, and what we apply to the networks. So the key idea is that given two networks, we linearize each layer of the networks, specifically of the second network. If you pick some ordering, so pick one of them and linearize each layer of that network with respect to its inputs about the first network's values. Linearization has been used in some of these settings already, and specifically for continual learning. And generally what people have done is they linearize the network outputs with respect to the network parameters. So entirely linearizing the function in terms of parameters. But we do something different where we do this linearization with respect to each layer's inputs. So it's a layer-wise linearization. And we're not assuming any linear relationship with respect to parameters. So the nonlinear interactions between parameters still hold. So what this looks like in practice is that the first two lines here are network computations for some network theta 0. So those remain exactly the same as before, the pre-activations and activations. For the second network, theta 1, pre-activations still remain the same because they're already a linear function of their inputs. The activations are now this first order Taylor expansion of the activation function, the ReLU function here, with respect to its inputs, S0, about the first network. So that's where the 0 comes from. I'll pause here if there are any questions about this key idea. This is mainly the idea of the paper.
Hi, Nikita, just a quick interruption. Do you mind admitting some attendees in the waiting room?
Sure, yeah, I see that. Okay, it should be good.
Perfect, thank you.
Okay, if there are no questions, I'll go ahead with how we actually implement this in practice. So if just a reminder that the Euclidean, so is there a question or anything? Okay. Just a reminder that the Euclidean distance that we're trying to compute, we only care about these output delta z's. And we can write that down for each layer's outputs. So these deltas for each output. So delta S is, this is just algebraic manipulation that I won't go into, but delta S is basically a function of the activations that go into this layer and the delta of those activations. And similarly, delta A is just a function of the deltas of the pre-activations. So we actually have this structure where we can propagate the deltas through the network. And specifically, we only care about the moments of these deltas. So we can just propagate the first two moments of deltas of every layer's outputs in order to get the delta Z finally. So just to take a step back and see why this is a good idea. So I hinted to a few of these things earlier. One thing that I said already was that nonlinear interactions between parameters are preserved in our case, unlike any other method if people are familiar with the neural tangent kernel, where the linearization of the network is done with respect to parameters. So they convert, that kind of approximation converts the network to something that is linear in its parameters. In our case, that's no longer true. So we allow nonlinear interactions between parameters, which could be important for performance and what the networks actually represent. Second, the network is linearized with respect to its inputs, and that actually allows for this moment propagation idea because we're able to leverage things like linearity of expectations, and we can do it using only moments and don't actually have to store any data points to evaluate the network on. And lastly, the expected FSD estimate is actually computed with just a single forward pass. In general, if we were storing data points and then had several batches of data points on which we wanted to compute these network outputs and then measure a distance, it would take several forward passes, and depending on the problem setting, could be computationally pretty expensive. But in our case, it only takes a single forward pass to do this computation, which is nice. Now, to actually implement this in practice, we need last two approximations to get an entirely parametric estimate. And in this case, in the case of MMPs, we call this a Bernoulli gated linear network. So the first approximation we need is to actually come up with the inputs to the first layer. So we can use, we can model the data distribution as a Gaussian, compute the moments of the inputs to the first layer are the data. So we can, which is why we need to model the data distribution as something. We can compute the moments of the data and sample from this multivariate Gaussian. The other thing that we need is the derivatives of the ReLU activations. These show up in the linearization, the linearization approximation that I had earlier. So because these are ReLU activations, they also have the structure being either 0 or 1. And so we can model these as Bernoulli random variables. So instead of passing pre-activations through a function phi, we multiply them element-wise with this Bernoulli random variable m. And the same thing holds for the deltas as well. One thing, and this m is a Bernoulli random variable with some mean parameter mu specific to layer L. One question is that how do we actually compute the average masks of these ReLU activation functions? And I won't go into too much detail here because I'll skip ahead to results after this, but one thing is that we could just compute the mask, whether it's a 0 or 1, based on the signs of the pre-activations that we already have. And in the paper, the results corresponding to this are called laughter. And the second way we can do this, if we do have the allowance in terms of memory and storage, is we can maintain a running average of how many times any given unit was a 1 or was left on during the training, and use that as the Bernoulli mean parameter. And that's what gives it this Bernoulli gating structure, and we call it BGLN. So I'll skip ahead. This is just summarizing sort of the algorithm that I already went over. So just to quickly go over it, all we need to do is store moments of the data and these Bernoulli mean parameters, sample from whichever random variable we need for each layer, and then propagate those samples through the network and compute a distance between the outputs at the end. And this actually becomes an unbiased estimate of our laughter-based FSD. And this is just representing that in terms of the actual computations. There's also a deterministic version of this that we can compute because we're only propagating moments. We can, instead of sampling from random variables, just use the moments of those random variables and propagate those through the network. And in that case, we can get an expected distance between outputs. This is useful for settings where stochasticity is not helpful. So it's nice to have a deterministic version of it. And again, these are computations that I will skip over for now, but they're all explained in the paper as well. One last thing that we evaluate is having classwise estimates. So in typical classification setting, for instance, all these random variables that we're using to approximate different information are done for, so far we've done them over the entire data distribution, but we could have a more fine-grained estimate and make all these approximations for each class. And that just multiplies our storage costs by the number of classes that we have. But it also gives us gains in performance. I'll just admit people. Okay. So how do we know if a computation is expensive? Is a specific metric you use. So one thing that we use is computationally, just we can measure the number of forward passes. That's not very complicated in our case because we actually just use one forward pass. In terms of memory costs, I'll skip ahead to the results that show this. So we can actually analytically, in the last column here, for each method, we can analyze what the memory cost for each method is. So in this case, P corresponds to the number of parameters of the network, and is the number of data points that a method might use to store, might store and then use to compute the FSD. And D is the dimensionality of the data. So, and C is the number of classes. So depending on your problem setting, there would be, some of these would be more expensive or not. Some are obviously very cheap just in general, but some of them are more or less expensive depending on what these exact values are. So we found that in these typical settings, like for continual learning, on this C400 benchmark, we have pretty good gains in memory. There are more results on this in the paper showing the percentage gains over other methods, while also, maintaining that goal that I mentioned earlier, where we have competitive performance with other methods and achieving state of the art on these. I see I'm out of time, but I'll just say quickly that there is some analysis on the different measures for how well we're estimating function space distances. So if anyone's interested in that, I encourage you to go and look at the paper. But essentially the point here is that we show that we're closer to the true function space distance than other methods would be. And this idea of linearization with respect to inputs actually helps a lot for that. And lastly, I'll just show quickly results on influence function estimation. This function space distance term actually shows up in influence function estimation, which is something that was shown by a previous paper from our group actually. And we sort of just use it as a test bed for our method to see if this can help in the setting as well. And the advantages in this case are that a typical way to measure this term for influence function estimation would be to iterate through your entire data set and compute this function, this term for the data set corresponding to P train. In our case, it's just a single forward pass. It's computationally much cheaper. And this is a case where there's some solvers for influence function estimation that don't handle stochasticity well. Which is why our deterministic estimate actually performs quite a bit better. These are the results for influence function estimation. The main takeaway here would be that we have higher correlations than other comparisons to the high correlation to the true objective that we want to estimate when we use our laughter-based approximation called BGLND here. And this, the plot on the right is a further application of influence function estimation in finding the fractions of corruptions or detecting corrupted data points. And again, while being very efficient, our method, the BGLN method, does get very competitive performance with other methods which actually iterate over the entire training data set and aren't as efficient. So yeah, that is the end of all I wanted to share. And I'm happy to take questions now or in the chat, or also feel free to email me if you'd like. But yeah, thank you for listening.